Hey everyone! Today we are going to do curve fitting with linear and quadratic functions. First, we're going to talk about linear functions. This lesson does require for you to pull up two Fathom files. The first one is called Linear Functions PS Form. And so go ahead and pull that up because I'm going to ask you to pause the video and do an exploration here in a few minutes. And you'll need that Fathom thing open. So first recall the point-slope form of a line or of a linear equation. We talked about that in our review. We have y minus y sub 1 equals m times x minus x sub 1. Remember that m was your slope of your line, and then this x sub 1, y sub 1 was just a point that was on the line. Now we're going to change this form up a little bit into a transformation form of a linear function. And I'm going to, instead of using y sub 1, I'm going to change that to a k. Instead of using m, I'm going to use an a. And instead of using the x sub 1, I'm going to use an h. And so you're going to see why here in just a few minutes, but I just want to highlight these are the only things that are changing. I'm just changing these variables because I'm going to talk about them in a little bit of a different way. So on the next slide, let's go ahead and write that transformation form again. Y minus k equals a times x minus h. Now I want you to open the Fathom file that I told you to earlier, the little linear functions PS form, and I want you to move the sliders for a, h, and k, and I want you to pay attention to how that line changes and jot down just your thoughts on what happens to the linear functions as you move those sliders. Pause the video, do that, and then come back and we'll discuss. Okay, hopefully you've had a good amount of time to explore. Now, the A was actually probably the easiest one to tell what was happening. When you changed the A, it changed the slope. Of the line. So when that a value was equal to 0, you probably saw you had a horizontal line. When the a was less than 0, you had a negative slope. When the a was greater than 0, you had a positive slope. And if I look at the absolute value of that a value, you kind of notice that the bigger, the steeper the line. So that's all you probably noticed with the a value. It changed the slope of that line. Now, I think with a line, linear functions, the h and the k are kind of hard to tell what's going on. What's driving what with the h and the k. Hopefully you noticed that when you moved the h and the k, you had both horizontal movement and vertical movement. Although it was probably difficult to tell which was driving which. So now we're going to talk about quadratics, and we're going to do an exploration with that one, and then we're going to come up with some generalizations about a, h, and k. So I want you to recall the vertex form of a quadratic. Remember I told you in that 2.1 lesson, the review of quadratics, that it's kind of my favorite one for modeling, and you'd see why later on. So the vertex form, you had y equals that a times x minus h quantity squared plus k. And the transformation form of the quadratic is just the same thing. Same thing. So now what I want you guys to do is go to the next slide. We're going to rewrite that one more time in this box. Actually, I want to take that back. Come up here. It's a little different. Not the exact same thing. They moved the k for transformation form. Take that k and move that k over. So you can see the only thing I'm doing here is subtracting the k, so I'm moving it from the right hand side and I'm moving it to the left hand side. So almost the same thing. Alright, so I'll have y minus k equals a times x minus h quantity squared. And you'll see why I like this transformation form with the count on the other side in just a moment. So open up the Fathom file called Quad Transformations. Same thing. When you pull it up, you should see a parabola. I want you to change the A, H, and the K using those sliders. Pause the video and come back here in just a few minutes, and let's talk about what you saw. Okay, hopefully you've had enough time now. The A value, what was it doing to it? Says the linear function here, but we need to change all of that. We're talking about quadratic functions here, so let's change that. What does the A value do to the quadratic function? Well, hopefully you noticed that the A value made the parabola steeper or narrower versus wider. If the A was 0, it was just a horizontal line. And then when A was negative, kind of same thing, but then it's flipping upside down. So you saw when that A value was greater than 0, parabola is opening up. When A value is less than 0, parabola is opening down. And then the value, the absolute value of the A, I'd say determined how wide the parabola is. All right. Now, the H and the K here were actually really easy to see what the transformation was. So the H here, right here, and notice this negative built in right here. The H was a horizontal shift. And when that H was greater than 0, it shifted to the right. And when the H was less than 0, it shifted to the left. But notice what you see. If the H value is 5, you see H minus 5, it moves to the right. If the H value was negative 5, you would see an X plus 5, and it would be moving to the left. Now the K over here, it was a vertical shift. Same thing, if the K was greater than 0, it's not moving to the right, it's moving up. And if the K is less than 0, it was moving down. And notice that negative built in. So recall whenever we had that vertex form, which was y equals a times x minus h quantity squared. If I move that K over, this negative being built in up here, the minus K that I've got up here in yellow, when I add that over, that's what makes you be able to see this vertical shift. And it's exactly like it looks. If you see a positive 8 there, then your parabola is going to move up 8 units. If you see a minus 8, it's moving down 8. But because this one right here is already on that side, it's not moving over, that's why it kind of behaves opposite of what you would think. So when you see x minus 3, it's shifting to the right. So you can see here with the h and the k, when I use this transformation form, that h and the k behave the same way. I feel like students often get really confused on why does the horizontal shift opposite, but the vertical shift is the same. I want you to see that they're actually behaving the exact same way whenever you have the y value and the vertical shift on the same side of your equation and your horizontal shift and your x value on the same side of the equation. So now let's use these models. Here I have a linear equation. Let's go ahead and put arrows on that. I got a linear equation that's passing through these 2 points, and I want to write a linear model, and I want to write it in that transformation form. So the a value, since this is a line, is going to be equal to my slope. So you have several options here to find the slope. You can use the slope formula. So remember, a slope formula is y2 minus y1 over x2 minus x1. You could just calculate the rise over the run. I think that's what I'm going to go with. So if I'm calculating the rise from negative 70 to negative 10, I rise 60 units to do that. And to run, I'm starting at negative 20 and I'm running over to a positive 2. So that would be 22 units. So my slope here is 60 over 22. Well, I can pull a 2. That would be a 30 over 11. And I believe that is all. So my a value is going to be 30 over 11. And now for my h and my k, well, I know back from my point slope form that h and that k, that's just going to be a point that's on this line. So I'm going to choose a point to work with. I think I'm going to pick this 2, -10. So I'll have y minus my k is my y value, -10, equals my slope, 30 over 11, times x minus 2. And to clean that up, my minus and negative, change that to a plus. So there is a model for the line. Of course, you could have chosen your other point if you wanted to use this other point. If you did, you'd have y plus a 70 equals 30/11 times x minus a 20, plus a 20, because it's minus a -20. So you could have had that as well. Since those are the only two explicit points that are given, they're probably the only points that I would choose to use. But of course, there's an infinite number of points on this line you can pick from. All right, now we're looking at this quadratic. Now, in the quadratic, remember the h and the k are going to be the vertex. So they give me the vertex, -1, 3. So here's my h, and here's my k. I'm going to start by plugging those in. So y minus the 3 equals some a value times x plus the 1 quantity squared. Plus the 1, of course, because I have minus a negative. Now to find the a value, I feel like a lot of my students get mixed up and they really want to use a slope formula here. They want to find the slope of the line that would go through these 2 points. They want to calculate the rise of the run, but there's not a slope for this parabola. That's not going to go work because this isn't a linear equation. It's very important that we take this point, recognize I have an x and a y that has to pass through this parabola, and I can use that, plug it in, and find my a. So we're going to plug in 1 and 1 for my y and my x. So I have 1 minus 3 equals a times 1 plus 1 quantity squared. Go ahead and use your order of operations. On the left-hand side, I have a -2 equals a times 1 plus 1 is 2 quantity squared. So I have -2 equals a times 2 squared is 4. And now I can divide by 4 to get that a by itself. So my a is a -2/4 or -1/2. And I was expecting the a to be negative because I know that my parabola is opening upside down. So that would tell me that a value is going to be negative. And the -1/2 means it's going to be a little wider than my parent function, which would have an a value of 1. So my final answer for my model here is y minus 3 equals -1/2 times x plus a 1 quantity squared. So now in dealing with these two different types of functions, quadratics, if you have an exact equation that is graphed, like here, you're only going to have one answer that is going to be accurate, one model. Whereas, remember, for a line, that h and that k can represent any point on the line, so therefore, there's a lot of different things that could be different here with my h and my k, but my a value has to be the same for my lines. But here for a quadratic, the h and the k are the vertex, there's only one vertex, and there's only one a value. Graphs, like I have here, most of the time. All right, so now what we want to do is take a look at a scatter plot. So that's really what this section is all about, is what if I'm given data? Because most of the time, we're not given perfect graphs. I'm given data, and I have to choose, do I want to use a linear function or a quadratic function or something else? There's definitely other types of functions out there that you guys all learned in Algebra 2. For right now, I'm only focusing on these two. Which one am I going to use? It says the scatter plot represents the total number of bacteria growing in a petri dish starting at 1 p.m. So if it starts at 1 p.m., that's going to be time t is 0. This is 1 p.m. Meaning at 1, that's going to be 2 p.m. And at 2, that's 3 p.m. and so forth. So it doesn't really even give me a 0 value. It tells me after 1 hour there's 20-ish bacteria, it looks like. And then the thing looks like it's growing kind of in a curve to me. So the first part here says write a quadratic model in the form of y minus k equals, should say a times x minus h, let's add in an a there, times x minus h squares that fits this below. So it even tells me to use a quadratic. There's really no choice. So what I'm going to do first, if I'm going to have to write a quadratic model, I'm going to draw one. So I'm going to try and fit a quadratic the best I can through these points. And I think that's the way it's going to have to go. So my quadratic over here, it would come up here on this other side, it looks like. Coming down. Something like this. Okay. So now we got to choose a vertex. If I'm making this up, I'm gonna put my vertex kind of like right here. And I think that is going to be the point 0, 18. So I'm going to set that as my h and my k. So my model so far is y minus 18 equals some a value times x minus 0 quantity squared. And now what I need to do is I need to know how wide this thing is. So I always tell my students that the further you go out, the better approximation you're going to get. So I think I'm going to go here to times 6. And if I measure this, it looks like it looks really close to 140. So I'm going to use the point 6, 140 as my point to plug in for x and y and solve for a. So I'll have 140 minus 18 equals a times x minus a 6 quantity squared. And now we've got to solve for that a value. So you probably need a calculator now. When I take a look at the left-hand side, 140 minus 18 is 122. Equals a times, oh, I messed up there. Let's clean this right side up. I'm plugging in 6, not changing my 0. Okay, so I have x changes to 6, that's the point I'm plugging in, minus a 0. So again, the 6, 140 is coming from that point right there. Alright, so 6 minus 0 is 6. And now I need to square that. So 6 squared is going to be 36. And now I'm going to divide by 36 on both sides to find my a value. So when I take 122 divided by 36, I end up with a 61 over 18, or 3.389 if I'm rounding to the nearest thousandth. So my model is going to be y minus 18 equals 3.389 times x minus 0 quantity squared. Now when you're modeling, when you're fitting model to data, there's going to be a lot of different answers that are going to be acceptable here. The important thing is that you show all of your calculations so that I can see here how you got your vertex, where you set your vertex, and then this other point that you've chosen to plug in to solve for your a and all of your work that goes along. So now that I've got a model to fit how this bacteria is growing in this petri dish, the next question says, how many bacteria will be in the dish at 3 a.m. using your model from part A? So let's think about this. If they told me that time 0 was 1 p.m., I need to figure out what x value am I plugging in for 3 a.m. So if this right here is going to be 8 p.m., if I were to keep on going, we'd find that 3 a.m. is going to be 14 hours since the experiment started. And so therefore, that is the x value I'm going to be looking for. So I want to know, at 3 a.m., this value right here would be 14. So we need to plug that in, and I need to plug it in for the x value because the x value is what represents the time here. So let's plug that in for my x value and see about how many bacteria I'm going to have. So I'll end up with y minus 18 equals 3.389 times 14 minus 0 quantity squared. Here, you're probably going to need a calculator. So 14 squared is 196. And let's multiply that by the 3.389. I have y minus 18 equals 664.244. And now I add the 18. And I get 682.244 bacteria. I should put in approximately here too, since this is a model. So if the experiment were left for the full 14 hours untouched, that's about how many approximately the number of bacteria that are going to be in the Petri dish, according to my model. Now the next question is a little different. It says, at what time will there be 200 bacteria? So here, 200 bacteria means that's a y value here. If I go back up to my model, my y-axis is the bacteria. So now I need to plug that in for my y value, and I need to solve for the x value to figure out what time. So I'll have 200 minus 18 equals, I say a, but it's actually the 3.38. I already found that from a model. 3.389 times x minus 0 quantity squared, where that 0 is going to be nice for this one. So when I'm solving this one, I take my 200, I subtract my 18, giving me 182, equals 3.389. And then x minus 0 is just an x quantity squared. So now I'm going to go ahead and take my square, or divide by the 3.389 to get the x squared by itself. I get 53.703 rounding equals x squared, but I'm leaving the full decimal that is a non-terminating decimal in my calculator, so that when I take a square root, I get an even more appropriate answer. So I'm gonna go ahead and take that square root, giving me 7.328. So that doesn't exactly answer the question. It just tells me what the x value is going to be. And notice when I take the square root solving an equation, I have to make sure I consider both the positive and the negative solution. So let's go back up to my graph. It's saying when x is 7.328 and negative 7.328, I'm going to reach 200 bacteria. So let's think about what this is happening, what this is saying. This is saying that when x is 7, which is right here, a little bit above that, that is when my graph is finally going to reach 200. So that's, say, 160 is here. If this were to keep on going, let's see, 140, 160, 180, about 200 would probably be here. If you were to keep growing, we're saying about here. So it's not perfect, but it's pretty close. There's a little bit of gap here. So what time would that be then? If x is 7.328, I'm looking at a little bit after 8 o'clock. Now the negative solution is the other side, because remember I'm using a parabola, so you've got negative solutions as well. So for this one, that solution is going to be extraneous, but sometimes both solutions are going to work. So here, this is going to be a little after 8 p.m. The quadratic function that you're going to use a quadratic model. Make sure you set your vertex first. Like here, we set the vertex at 0, 18. And then you're going to choose a point. My advice is far away from the vertex so that you get a really good, decent shape, a good A value. Plug that in for your point, solve for your A value, and then you get your model. All right, so here's what I want you to do next. You have a full-on Fathom problem. You're going to open a blank Fathom file and insert the data below and see if there's a relationship between the total fat grams in each sandwich and the total calories. So really what you're going to be putting in to fathom is this information here. You're going to take a look, decide if it's linear or quadratic, come up with a model, and then use your model to estimate how many calories would be in a sandwich that contained 40 grams of fat. So go ahead and take some time to put that in Fathom, make a scatter plot, which you actually have right down here. Pause the video while you do that, and then we'll come back and talk about it. Okay, hopefully you had no problems putting that into Fathom, getting your scatter plot, taking a look, and making a decision. So you could go either way here with the linear or quadratic. If you go linear, it's kind of looking like this would be your line best fit, something like that. If you go quadratic, it does kind of dip down here right around 7-ish, maybe 9-ish. So I could see where you might have something like this going on. Since we did quadratic in the last example, I think I'm going to go ahead and choose to work with the linear model for this one. So I'm going to draw a line best fit. That's going to be our first step, is just to draw a line that best fits the data. I don't know if I love that one. Again, you can just draw it as many times as you want. It's your line, so you can draw it as many times as you want till you decide you like it. I like that one better. Alright, so linear it is. Can you come up with a model? Sure I can. So for a line, I'm going to first try and get a slope, and I'm going to get kind of far out with the points I choose on my line. So this one, I think that is going to be the 0.8, 325. And for this one down here, looks like it's 33,600. So when I do my rise over run, I'm going to get my rise to be, so my change in y, I do the 600 minus the 325, and I get 275. Over the change in the x, I'm going to do the 33 minus 8, and that gives me a 25. So now I take the 275 and I divide that by the 25. That goes in nice and easy. I get a slope of 11. So that's my A value right there. And now I just choose one of the points to work with. I think I'm going to choose this one because it's smaller numbers. So my model is going to be y minus 325 equals 11 times x minus 8. Again, lots of different points you can work with here. As long as you show your work for your slope and how you're getting that for your A value, you should be good in showing that your model is a decent one. So the next thing says, can you estimate how many calories would be in a sandwich that contained 40 grams of fat? So when I see this 40 grams of fat, based on what I've got for my model, I have total fat here as my x-axis in grams. So I got to make sure I plug in the 40 for my x, and I'm solving for y, which is the total calories. So I get y minus 325 equals 11 times 40 minus 8. And now I just solve for y. So I have y minus 325 equals 11 times 32. When I take that 11 times the 32, I get 352. So I have y minus 325 equals 352. Add that 325. I get y is equal to 677. And my units here are calories. I'm going to put in approximately here because I'm using my model that is approximated for the data that I have. So now, hopefully you guys feel really comfortable curve fitting with linear and quadratic functions and data. Just to review, for a line, it's a little bit easier of a process. Just choose 2 points. It really doesn't matter how far away they are. It's just a habit of me to choose some things that are far away. And then find my A value by using that slope formula or rise over run. And that will give you the A value, and then any point that's on your model is going to be good for that H and that K. So now you guys are set to do the problem set 2.2 and give this some practice.